In this slide, we're just going to give a basic idea of hypothesis testing. So we'll start with a research question. We have a historical average of 35, and we want to know if there's been some change in either direction. Also, we're going to assume a population standard deviation of 5. So formulate the hypothesis. Our research hypothesis is that the population mean is not equal to 35. Again, it could be higher than 35 or lower than 35. We're just hypothesizing that it's not equal to 35. The null hypothesis then is mu equal to 35. So next we get a sample and obtain sample statistics. So let's say we took a random sample of 25 hours and the sample mean was 31 units per hour. So now we'll compute the mean and standard error for a sampling distribution. So our hypothesized mean was 35. That's going to be the mean of the sampling distribution. The standard error will be the population standard deviation divided by the square root of n. So we'll have 35 and 1. So now we'll sketch that sampling distribution. With our sample size of 25, that's going to be a bell curve as long as we don't have any outliers in the population. So where we have it, a bell curve with a hypothesized mean of 35, a standard error of 1. Make sure you note that the random variable is the sample mean, which we know is a bell curve due to the central limit theorem. Okay, so to test the hypothesis, what we want to know, we had a sample mean of 31. Is the fact that that sample mean is 31 sufficient to conclude or to be confident that the productivity has changed from that historical average of 35? The answer is yes. That 31 is 4 standard errors below the hypothesized mean. And by now you should understand that if we're 4 standard deviations or 4 standard errors away from the mean, there's just not a very high likelihood of having a value that far away from the mean. It would be extremely unusual. We can't be certain that it's not 35, but we can be highly confident because the area below 31 is going to be very close to 0. This wording here where it says if the mean of the population is 35, the sample mean of 31 would be extremely unusual. In later slides we'll start talking about that as the p-value. So you might want to consider just the meaning of that. You start with if the mean of the population is 35, then we're going to compute the probability that we would get a sample mean, in this case of 31, and how usual or unusual that sample mean would be, given again the hypothesized mean is true, that it really is 35. In this case, we would almost never get a sample mean of 31 if the real population mean was 35. Let's suppose we had a sample mean of 36 instead of 31. If 36 is not equal to 35 either, but it is the fact that the sample mean is 36 enough to be confident that the productivity has changed from the historical average of 35. The answer is no. That sample mean is only 1 standard error above the hypothesized mean. So using that same kind of phraseology, if the mean of the population is 35, we would obtain a sample mean of 36 about 16% of the time. Remember, we're talking about 36 or more, so if we're 1 standard deviation away from 35 to 36 is about 34% of the data, or 0.3413 if you're using the Z table. And that would leave about 16% in the tail. If the population mean is 35, there's about a 16% chance of getting sample mean above 36. Therefore, what we're going to say is it's plausible that the population mean is 35, that there has been no change. It really isn't time to sit up and take notice because we have 36. And that difference between 36 and 35 could simply reflect random error, the fact that we're going to get different different sample means from sample to sample anyway.